Good evening, everybody. Today we will discuss the next topic, that is chiral catalyst for the asymetric synthesis. The first example is the stereochemistry of the Sharpless asymetric epoxidation. So, Sharpless asymetric epoxidation means we are doing an oxidation of an alkene, and now we are creating new chiral center and two new functional group. And here the chiral catalyst is prepared by using a chiral ligand. Here we used the chiral ligand as plus or minus diethyl tartrate, and which will combine with the titanium catalyst. So we will get the chiral catalyst as titanium isopropoxide, which is clubbed with the ligand as diethyl tartrate. So our starting material is allyl alcohol and the product is an epoxide, and this product epoxide will further undergo the reaction and we will get the alcohol Okay, now we are moving into the experiment, the chemical reaction. See, this is the allyl alcohol, our starting material, and you know that the allyl alcohol means it is a sp2 hybridized carbon atom is separated by a sp3, the hydroxyl group, and sp2 hybridized carbon atom is separated by a sp3 hybridized carbon atom. And since it is a planar structure, there are two possibilities for the attack of the nucleophile or the reagent can approach in the both sides, either from the top or from the bottom. So this phase we call it as Si phase or Re phase. That is clearly mentioned in the slide. Then first of all, we have to produce the chiral catalyst by mixing titanium isopropoxide and diethyl tartrate, which is acting as a ligand, and it is an optically active ligand. So it is represented by DET. It may be plus or the minus. And we also used a oxidizing agent as tertiary butyl peroxides. So the result, if you are using minus DET, that means minus diethyl tartrate, then we will obtain the structure, the final product as the epoxide, but the epoxide oxygen is on the top face of the plane. Now if we use the plus DET, plus diethyl tartrate, our epoxide is formed in the downward direction. See the slide. So depending upon the chiral activity of the ligand diethyl tartrate, the product may change. If it is minus DET, the epoxide formed in the upward direction, that is epoxide oxygen on the upward direction. If it is a plus DET, then oxygen is in the downward direction. This is the actual Sharpless asymmetric epoxidation. So the name indicates that the final product is epoxide and the starting material is an allyl alcohol. Now we are moving into the actual the reaction between the ligand and the catalyst. See here, our ligand is diethyl tartrate. This is the structure of the diethyl tartrate. We already studied the optical activity of the tartaric acid, and we know that there are two chiral center in the tartaric acid, and the configuration of we can determine the configuration of the tartaric acid, chiral center of the tartaric acid. Now here this is only an ester, diethyl tartrate. And the optical activity of the diethyl tartrate, here it is L plus. Okay, plus. Then it will react with titanium isopropoxide along with a hydrogen peroxide, substituted hydrogen peroxide. We will form an asymmetric complex as the catalyst. This is the structure of the asymmetric chiral catalyst. Then see here, this is a dimer, and here in the dimer we know that the titanium always form a octahedral complex. So in the octahedral complex, two of the position in the octahedral complex is occupied by the titanium isopropoxide, and the remaining 4 positions are compensated by the diethyl tartrate. Now again it is clubbed with the other titanium complex. So this is the final structure of the catalyst, and if the allyl alcohol approach towards the chiral catalyst, one of the isopropoxide is removed, and this is the actual structure of the chiral catalyst. See here, the titanium is represented by the red color. You can see the two titanium element, and which is coordinated by, if we take the single titanium element, so the two of the ligand position are occupied by the OR, that is isopropoxide, and the remaining 4 position are attached by the diethyl tartrate, and titanium atom bridged by the 2 tartrate ligand and retain 2 of the isopropoxide ligand when the oxidizing agent is added to the mixture. Here the oxidizing agent is the butyl peroxide isopropoxide ligand. Then one of the tartrate is removed. One of the carbonyl group of the tartrate is removed, and which is complex. This complex react with allyl alcohol, and it again react with the hydrogen of the peroxides. Then since see the transition, see the structure of the complex which is attached to the allyl. See in the oxidation, oxygen is added from the peroxide, and peroxide is in the lower to the plane of the allyl alcohol. That's why if you are using the plus diethyl tartrate, we will get as the oxygen atom in the epoxide which is away from the observer. I hope that you understood the concept. Thank you.